Let me briefly go over what we were doing for the higher order elements in the rectangular and the general quadrilateral case. Um, we were talking about this Lagrange family of polynomials that you can use to interpolate the displacement over any quadrilateral element. Now this element is in the parent domain, and we already know that the linear shape functions we can use in one dimension in both C and eta. So if you multiply them together in C and eta, you will get the shape functions for this Q4. That's how we generated the Q4 shape functions. And then this Q9, let me pull up what these Q9s look like. So this is what the Q9 shape functions look like. This is the corner node 1, 1. It's the value of the shape function here is 1. At every other node, it's 0. So if you take a look at this element, there's a node in the middle also. So any shape function has to go to 1 at their node and 0 everywhere else. So you can take a look at these 4 corner shape functions. These are 1 at the corners and 0 everywhere else. 0 at the other nodes, not everywhere else. But these are the mid-side nodes, and these are clearly not bubble functions. We talked about that last time. So these are not bubble functions because if you stack them next to each other, you will have discontinuities along the element edge. So this is the only bubble function that Q9 has. Okay, so these are the 9 shape functions for the 9 nodes in Q9. And another picture, if you see this picture is of the sum of the shape functions minus 1. So basically what I'm plotting here is, let's see if I can pull that up. So this is how we generate the plots for these Q9. You have 3 shape functions. These are the 3 Lagrange shape functions in C. And these 3 shape functions we already derived right here, 1, 2, and 3. These are the 3 Lagrange shape functions in C, and similar shape functions in eta. So those are the 3 shape functions in eta. And then for the corner nodes, you can multiply the corresponding C and eta functions, and you can generate, these are the 4 corner shape functions. These are the 4 mid-side shape functions, and 1 N9, which is the bubble shape function. So if you were to add all of those shape functions, we know that it should add up to 1. Right? Sum of all the shape functions should be 1 in a finite element formulation. So what I'm plotting here is sum of the shape functions minus 1. So if the sum of the shape functions is 1, then what I should get in my plot is 0. And indeed, if you look at the numbers, these are 10 to the power minus 16. So 10 to the power minus 16 is really small, and all the little variations that you see in the color is only because of numerical, the round off errors that MATLAB makes. So it's pretty much 0 everywhere else, 0 over the entire domain. So these are Q9s. Let's take a look at Q16. So in Q16, you will have, let's go back to the figure. This is Q16. You have 4 nodes in both C and eta, and the Lagrange shape functions, we already know how to generate them. For example, for this node, we will make sure that this function goes to 0 at this point, and at this point. So if you do that, you can straight away code that thing up in MATLAB. For each of the 4 shape functions in C and 4 shape functions in eta, and then you start taking the product. If you start taking the product of all that, and let's see if we are again plotting the sum and all that. So let me see what this one looks like. So again, you can see that the sum of the shape functions is 1 everywhere. Again, the numbers are 10 to the power minus 16. And the shape functions for the Q16 look like this. Again, we have the 4 corner shape functions. We have 2 mid-side shape functions. One for this node, and so basically each edge has 2 middle nodes. Therefore, these 4 and these 4, total of 8 shape functions are mid-side shape functions. Those correspond to all these nodes. This node, these two nodes, and so on. It's the middle 4 that are actual bubble functions. So if you go back to the figure, you can take a look at all these 4 shape functions in the bottom row. These are pure bubble functions because they go to 0 at the edge and they are 1 at their specific node. So again, since these are bubble functions, when you are implementing this in a finite element code, you can statically condense them out, and you can get some more efficiency from your program. So, all right. So this is how you generate what is called the Lagrange family of shape functions of elements. Lagrange family of higher order elements for quadrilaterals. And we also saw last time that the actual order of polynomial that a certain Lagrange family approximates is represented by these sort of terms. So these terms are representing a degree of polynomial that your element is going to approximate up to. So Q4 has 4 parameters. It does this. Since Q9 is quadratic in C and quadratic in eta, therefore it has all these terms in it. But Q9 is complete only up to the quadratic term. It does not include the x cube and the y cube term. Therefore, the order of convergence in displacements for Q9 is going to be order h cube, meaning if you half the size of the element or double the number of nodes, your displacement will go down by 1/8. The error in the displacement will go down by 1/8. Half the size of the element, error goes down by 8 times. So that's the h cube displacement error for Q9. So similarly, you can keep on increasing the order in C and eta, and you will see that these are the types of things that are getting approximated. So here's the question. If I have a Q9 element like this, can I connect it to 2 Q4 elements in a mesh? Why is that? Why can't I do that? Okay, so let's take a look. So if you remember from one dimension, let me ask you a simpler question first. Let's say I have this one-dimensional element, which is the 3-noded one-dimensional element. And can I connect it next to a 2-dimensional element? I can, because the shape functions are something like this, right? So this is a continuous shape function over the entire domain, and therefore I can use continuous shape functions because their derivatives are well defined, and their derivatives are square integrable. This is the H1 thing that we were talking about long back. Since this is a continuous function, I can do that in 1 dimension. But the same thing in 2 dimensions looks something like this. So for this Q9 element, the shape function at the edge is something like this. It does some variation here, but the edge is curved. If you were to put together the shape functions for these 2 Q4 elements, what would that look like? Something like this, right? So if you were to connect these two, this straight edge would not match up with this curved edge, and you would have a discontinuity, unlike the one-dimensional case. That's why you cannot connect straight away a Q4 to a Q9, 2 Q4s to 1 Q9. So when you assemble all of these elements, they have to form a continuous global function. And if you remember from long back, when we were talking about T3 elements, let me see if we can pull that up. Finite elements, discrete factorization right here. So if you remember this, if you choose all the triangular elements, and if you were to assemble all the triangular elements in the big mesh, the shape function for one node looks like a tent, but it is continuous. Even though it has discontinuous derivatives on the edges between the elements, the shape function itself is continuous. So it satisfies our criteria that we can use only continuous shape functions that have the first derivative, which is square integrable. So all these types of shape functions are in H1 of omega. But this shape function that we have just talked about, this is not in H1 of omega. So this is uh, not the way to connect it. So this actually sort of inspires what we are going to talk about next. The serendipity elements. These serendipity elements are actually were initially sort of developed so that you could connect these two different types of Q4 and Q9 with one edge node. So the way we connect these serendipity elements is by adding nodes only on the edges. We don't add any nodes inside. Okay. So the first step is we start with a Q4. This is the exact same Q4 between the Lagrange and the serendipity families. So Q4 remains the same. And if you look at the shape function N1, that looks something like this. And what we are going to do is we are going to add a shape function to this Q4 element by creating a node at 5. So when we do that, we have to take into account that the shape functions for N1, it has a value of half here, right? So we have to modify our original N1 shape function by subtracting half of N5. So let's actually do that on the MATLAB code. That might. So this is Q8. So if I were to, okay, let me place a breakpoint here, F5, and then I'm going to create the 4 shape functions for Q4 first. So N1, N2, N3, N4. These are my 4 corner shape functions. This N5 is a Lagrange type shape function. And if you look at this figure, this Lagrange type shape function is created by taking this shape function, which goes to 1 at node 5 and goes to 0 at the 2 other nodes, and multiplying it with a linear shape function in eta. Okay, so if I multiply those two out, I should get a shape function for node 5, which goes to 0 everywhere else, but goes to 1 at node 5. So that's your shape function for node 5. And now let me see if we can plot. Okay, well, I don't need the breakpoint anymore. So let's see what happens. So these were the 4 shape functions that we had just created, N1 through N4. And this is the N5 shape function. And what I need to do is to, if I just can't add this N5 to my set straight away, because that will mess up the condition that some of the shape functions need to go to 1. These 4 shape functions go, if you sum them up, they go to 1. But if we want to add this shape function, then we must subtract half of this shape function from N1 and half of this shape function from N2. And if we do that, let's see what happens. So what I'm going to do now is going to modify N1 to be N1 minus half N5, and similarly N2 to be N2 minus half N5. And if we do that, run it again, and this was supposed to be, some of the shape functions is supposed to be 1, but let me explain this first. So this is N1 after you modify it by subtracting half of N5. This is N2 after you modify it by subtracting half of n5. The sum of these 5 shape functions, what will that be? It will be 1 because the original shape functions, original 4 shape functions that we had, they sum to 1. If I'm going to add a new shape function to that and subtract half and half of that, then I should recover what I had originally, 1. And let me see why it's not plotting 1 correctly, because I have not included n5 in this. So if we do that, so I'm plotting the sum of the shape functions n1 through n5. Now if we do that, you can see that this is indeed 1. The sum of these 5 shape functions is indeed 1. Okay. So similarly, now that we have added this node, we have this special type of element now, which has 4 nodes on the corners and 1 node at the middle side. And the sum of all the shape functions still go to 1. This element I can use to connect these types of things. So for example, if you go down here, there is a Q4, there is this Q9. So I'm connecting one Q4 with one Q9 with this type of a transition element which has one middle node here. This is a valid connection because the interpolation is linear between these 2 nodes here. The interpolation is quadratic between these 3 nodes here. So there are no discontinuities if you connect it like this. And the sum of the shape functions go to 0 or go to 1, which means that if you keep on refining the mesh, you will get convergence even with this weird 5-noded element, transition element. But we can keep on adding these types of nodes to this element. So let's try to add this node, which is n8. Okay. So if let's see what happens if we add n8. So I'm adding this shape function n8 now, and I'll be modifying n1 to be minus half of n5 and minus half of n8. And another n8, so n8 is the shape function for this one, which means that n1 and n4 need to be modified. Okay, so that's what I'm modifying here. I have modified n1 and n4, and let's see what happens now. I should plot these things. So you see that now I've added this n5 and n8. I've modified my n1 shape function, n2 and n4. n3 is only the original function right now. So this is, and if you take a look at the sum of the shape functions, that's still exactly 1 everywhere. Okay. So finally, you can add all the middle side nodes, and what we would get is this and this. Okay, so I need to uncomment these 2. So these are the Q8 shape functions. These are the 4 corner shape functions for Q8, and these are the 4 mid-side shape functions for Q8. There is no bubble function in Q8 because there are no nodes inside the element. Okay, if you take the sum of all these shape functions, that sum goes to 1 everywhere in the element. So this is how we create a general serendipity class of elements. These serendipity class of elements, they don't usually have, actually they don't have a node inside the domain. They just have extra nodes on the edges. So this is a Q8 element which is complete up to quadratic terms. It is complete up to x square, xy, and y square. So the order of convergence of this Q8 is going to be the same as Q9. And another point to make here is that we know that Q9 has 1 bubble function. So if we condense that out, we get back, quote, 8 nodes. That 8-noded element is not the same as this Q8. Okay. So, all right, so we can keep on adding these nodes the same way. As soon as we add, we can create Lagrange shape functions for each of those middle side nodes. This would be a Q12. And just subtract, if you add one node here, you have to subtract 2/3 of this node from this shape function and 1/3 of this node from this shape function. So if you're adding a shape function, you make sure that you subtract the correct amount from the corner shape functions. That's how we create the serendipity class of elements. Yes?
You said that when you converse Q9 element, it's not the same as Q8.
Uh-huh.
So the question is why, and if you mean the result, if we disregard the bubble function in our analysis,
Mm-hmm.
The result would not be the same as Q8?
No, if you because you cannot disregard the bubble function, because then your shape functions would not sum up to 1.
No, I mean in the final analysis, we don't account for the displacement for the bubble node. We just
No, you statically condense it out, but you are still taking into account the bubble function.
That's what I'm saying.
Right.
We just
Okay, so the main reason that it is not equal to is because if you take a look at the terms that Q9 approximates, there is this Q square, X square, Y square term sitting in there. And the corresponding term for Q8 is not there. So the order of approximation, the polynomial approximation that Q8 and Q9 use is different. Okay. And another reason is that all these Q8 functions we created by adding a mid-side node, but in the other direction we were using a linear shape function. This kind of a construction. So this is a different construction from the Q9 element. So so yeah, this is how we construct the serendipity class of functions, and there are actually explicit formulas for these that are given in your book by Zinkiewicz and Taylor and by Reddy both. So if you let me just plot these Q12, which are serendipity class of functions. So you can see that they sum up to 1 everywhere, and we have these 4 corner shape functions, and for each edge we have 2 shape functions. So these are at 1/3 and 1/3. Okay, so these are all over the parent element in C and eta. So we get all these shape functions, these 12 shape functions for the serendipity class of shape functions. All right, so in serendipity class, if you keep on increasing the order, let's say Q8 was here, if you add, go to the next level, which is Q12, that Q12 includes these terms right here and these terms right here. So you've added 4 nodes and you've added 4 polynomial terms. Okay, so you're missing out on all these terms that are inside here, and therefore you actually don't gain much by using this serendipity class of elements anything beyond the cubic order. So this Q12 will be complete up to this cubic order, right? It has this Q8 only has these terms, but the Q12, it has x cubed, x square y, xy square, and y cubed. So it is complete up to cubic term, which means that displacements will go by the error order of h to the power 4. You have the element size, error goes down by 16 times. Okay. All right, so you can keep on increasing these order, but you don't gain much. And if you do want to gain anything, then you would have to add bubble shape functions in the middle of the thing to include any of these terms. So that's that. Okay, so here's another question. What would you do to connect this Q4 to these 2 Q4s? Can I use this serendipity class of 5 element to do that? How many think yes? No, you can't, right? So, and the way to see that is So if you were to take the shape function for the Q5 that we have just generated, that would be a curve here. And both of those Q4s are going to be like this. Right? So you cannot match these two together. So if you do want to connect a Q4 like this with two Q4s like this, then you would have to construct a new type of a 5-noded element where you can use the same type of idea, the same serendipity idea, but instead of choosing this as your bubble function, if you remember, we chose this as our bubble function for N5. Instead of choosing this, we can choose this, this alternate bubble function, which actually has straight edges. Right? So if we choose this bubble function, which actually has straight edges, and we use the exact same serendipity idea, we will come up with a 5-noded element that you can then use to connect these two Q4s to this single Q4. Does that make sense? Okay, yeah. 3 triangular elements where? Here, you mean? That is correct. You could use 3 triangular elements. Yep, that's correct. And how about this? How do we connect these things? To connect this with this, we would need a transition element like this, and that transition element would need to have a weird type of a, let's do that. So this is the transition element that we are trying to create. It would have the regular bubble function on this side, and it would need this hat shape bubble function on this side. So if you construct this kind of a transition element, then you can sort of split these two apart and plug this thing in there. That would be a valid connection, because in this case there wouldn't be any discontinuities at the element boundaries, right? Okay, so that's more or less about the how to construct Lagrange family of shape functions, how to construct serendipity family of shape functions. Yeah.
When running in the program, you're more or less saying element by element. You wouldn't get any error if you try matching what would happen.
Okay, so yeah, in a program, in a MATLAB program, you could construct a mesh that would look like this. So this mesh would actually violate our weak form that depends upon the fact that our derivatives of the shape functions are square integrable. So 2 things could happen. One thing is that if you sort of keep on refining the mesh, your stiffness matrix will keep on becoming singular. And that means that your element or your mesh is becoming unstable. So you would predict very high displacements. On the other hand, maybe things could lock up. That is, the eigenvalues of your stiffness matrix might go very high, which means that the mesh will behave in a very stiff manner. So essentially, you have no way to conclude that if you use this philosophy, that you are getting some answer which is reasonable, right? If you use this mesh, all your error measures thrown out of the window. If you use a uniform Q4 mesh, you have some confidence in your solution that your solution is within a certain error of the exact solution. And if you refine your mesh, you will get to the exact solution. If you use this kind of a mesh, we'll talk about that a little later today. This is what is also called a variational crime. So, and this is not a term that that we coined. This is something from a professor who did finite elements at MIT. And on the last page of your handout, we have a quote from him today too. So we'll get to that. So that's what happens if you connect elements like this. All right. So another way to to construct higher order elements is by using hierarchical elements, hierarchical shape functions. And what does that mean? Let's say, going back to the one-dimensional case, you have this 1D shape functions. You can just keep on adding as many bubbles as you want to this shape function. Okay, all these shape functions, they satisfy all our conditions of H1, meaning they are continuous, they are square integrable. So you can add these two shape functions to this set, and what you would get is that U of X is sum of n over alpha times dE alpha. This is something that we had from this is our regular finite element approximation. To this, we are going to add sum of beta from 1 to whatever n bubble function beta times some constant beta. So the new approximation, when we add a hierarchical shape function, becomes like this. This was the old approximation that we had. As long as we keep this, we are guaranteed convergence. If we stack on a few extra bubble functions, then it is not going to hurt us. Another point is that these d alpha, they are actually the displacements at the nodes. But these c beta, these are not, these are just some nodeless parameters. This is something similar to your Ritz approximation, where we said A times H. So you can keep on adding these bubbles to your approximation. And the benefit of this is that, let's say the solution that you're trying to capture, maybe at a crack tip, has some sort of a singularity. So you can stack on some bubble functions that actually capture that singularity. And when you use that complete approximation, your finite element method is going to give you a solution that will have the least possible error from all these shape functions combined. Okay, so this is one set of bubble functions that you could use. This is another set of bubble functions. Clearly, these bubble functions go to 0 at the nodes, and they are non-zero somewhere in the middle. How about this? Is this a valid bubble function? It's not a valid bubble function because it is discontinuous. So even though it goes to 0 at the nodes, since it is discontinuous, it is not in H1, right? If we take the derivative of this shape function, the derivative will have a Dirac delta here, and you cannot do a square integration on Dirac delta. So this is not a valid choice for a bubble shape function. All right, so the similar idea holds true for 2 dimensions also and 3 dimensions also. In triangles, let's say you start with a T3 triangle, and you add a bubble that goes to 0 at all the 3 edges. So this is sort of a bubble that goes to 0 at all these 3 edges, and it is non-zero in the middle. And similarly, you could actually subdivide the triangle. This is also a way to do mesh refinement. You start with a coarse mesh, and you subdivide your existing mesh into smaller and smaller parts, and then you use a hierarchical set of shape functions. So that way you don't have to compute all the results all over again. And the same idea for rectangles. You can have bubbles in this direction, bubbles in this direction. If you multiply those two, you're going to get a bubble over this domain. So just keep your original shape functions and add any number of bubbles you want. Okay, and since these are all bubble shape functions, you can actually statically condense them out. So the size of the stiffness matrix also does not go up. Okay, but there are some extra element level calculations if you use these hierarchical types of higher order elements. So I think I've already mentioned most of these things. You keep your base shape functions that will guarantee convergence. Bubbles can be condensed out statically, so your size of the problem does not become larger. Sum of the shape functions holds only for the base functions. Only if you take these base shape functions, they will sum up to 1. If you add on these, obviously it will not sum up to 1. Chronicle Delta is also a very useful property that we've talked about before. This is saying that if you take the shape functions for two nodes, uh, the shape function for this node will go to 1 at this node and 0 everywhere else. That's the Chronicle Delta property of finite element shape functions. So that property is still maintained because the existing shape functions go to 0 at every other node. These bubble shape functions go to 0 at all the nodes. So this property is also still maintained. Okay, so that's basically sort of the gist of how you would construct higher order elements in Lagrange family, in Serendipity family, and the hierarchical higher order elements. So these are the three types of higher order elements people generally use. And related to this hierarchical elements, there is a class of elements called incompatible bubbles. And just like I said, this is also a variational crime. That was a quote according to Strang. So the idea behind this incompatible bubbles is that we want to use general Q4 elements because they are convenient and you can easily code them up, and maybe you won't find them as convenient but the very first time you code them up, but they are indeed quite convenient to code up. But the problem with these is that if you use a coarse mesh, you do not get good results for bending dominated problem. So very similar to your T3 element that you saw for your homework 5. If you use a coarse mesh, the amount of displacement that you get is not much. And the reason for that is right here. Let's say you have a rectangular Q4 element and you apply a bending moment to that just one element, okay? Um, since this rectangular element can has only this type of a deformation mode, this deformation mode does not capture bending exactly. If you wanted to capture bending exactly, you would have to capture this sort of a curve here on these two edges, right? If you let's forget about this Q4 element. If you have a two-dimensional plate, if you apply a bending moment like that, it should show a circular curve, a constant bending moment, right? So since this element is not able to represent this type of a mode of a deformation mode, it locks up, and we do not get accurate displacements with this. So the idea to correct this was, let's add these shape functions which are curved on these two edges and remain straight on this. So this type of a shape function would be like this, right? This goes here and this goes here. But unfortunately, and similarly, you add the other shape function in the eta direction also. If you switch around your bending in the eta direction, you have these two incompatible bubbles. So strictly speaking, these are not even bubbles because they don't go to 0 at the edge, right? But if you add them, you will be able to model this type of a deformation mode. And since these are not bubbles, when you stack them next to each other, you will have discontinuities. So that's something like here. Let's say you have a patch of 4 elements. Each of these things over each of those individual elements, they have different coefficients. So since those shape functions have different coefficients between these two elements, a gap or an overlap might open up. And just like we talked right now, since this is not continuous along this edge, the derivative of this shape function would be Dirac delta on this edge, which means it is not square integrable and it is not a valid choice. So people tried to find out ways of how you could use these two shape functions because they are helpful in bending problems. We do not want to use the finest mesh for the triangular elements, 2,500 elements, just to solve a cantilever beam problem, right? If we have to use 2,000 elements for a simple problem like that, then we are in trouble. So that's why people try to use very coarse mesh, 5 elements, just add these two shape functions, and let's try to make sure that now it actually passes what is called the patch test. So the way to do that is this. people were able to show that if you add these two shape functions to a rectangle, to a rectangular element or a parallelogram, then you can ensure that it can represent a state of constant strain. This was our test that we had formulated earlier, that any element you develop has to be able to represent constant strain and constant stress. Okay. So if you use rectangular elements and parallelograms, then adding these two is fine. But as soon as you have an isoparametric deformation, something like this, if you have an isoparametric deformation, these two shape functions will not be able to represent a state of constant strain. So the idea of Robert Taylor, that's the same Taylor from your book, Zienkiewicz and Taylor, was that we will modify our B matrix slightly. So if you remember, the B matrix was to calculate the B matrix, we needed these derivatives of the shape function with respect to x and y, the real coordinates. And we calculate those derivatives by using a Jacobian inverse transpose times the derivatives in the parent coordinates. So instead of calculating these derivatives at the 4 Gauss points using this formula, we will modify this formula by calculating the Jacobian only at the center and divided by the actual Jacobian, the determinant of the Jacobian at that point, and multiply that with the same determinant at the node. So what we are saying here is that we need to calculate our B matrix, and strictly speaking, the way that we should have calculated our B matrix was Jacobian inverse transpose times derivatives of shape functions. And that would have held at all these 4 2 cross 2 Gauss points. So instead, we are now saying that we'll go to the center Gauss point, which is sort of related to reduced integration. We'll calculate our Jacobian there, and we'll also calculate our determinant of the Jacobian there. And now, using those two quantities, we will just use the Jacobian and the determinant from the center and calculate these derivatives at all these 4 points using this J inverse transpose and this J naught. And if you do that, you can make sure that adding these two bubbles to your shape function, even if there is an isoparametric distortion, even then it passes this patch test, which says that it can represent constant strain. So this was a sort of a trick that people used to be able to use, let's say, just 5 elements for a cantilever beam problem. And if you have these two extra shape functions in there, and you use this reduced integration trick on part of the terms, then you can pass the patch test, and that element would converge. Okay. So this is sort of the famous quote that is related to this. So Gilbert Strang is a professor at MIT. One of the very very fundamental books about mathematical analysis of finite elements was written by him. And actually, if you go to YouTube and maybe just search MIT Strang finite elements, it says it didn't find anything, but they're actually right here. So this is a course which is, has anybody used MIT OpenCourseWare before? No? So partly maybe, yeah. So this is a course that they have this system where they have put most of their courses online, available for free. And if you go to the lectures, they have all these 49 lectures from 2008 there. You can probably take a look. So this is the Gilbert Strang, who quoted Robert Taylor for using these types of incompatible elements. since the first mistake that you're making is by actually using something that is not a bubble, something that violates your principle of weak form. So it is technically a variational crime. So we've heard that saying, right? That two wrongs don't make a right. And so Gilbert Strang poked fun at Taylor that two wrongs do make a right in California. And this is in 1973 in his book. And so maybe what, 16 years later, Robert Taylor found a way to get around that and showed that this is actually a valid choice, that these two shape functions are a valid choice for a different type of a formulation, which is a mixed formulation. And we are not going to go too much into detail about a mixed formulation, but then he sort of wrote back to him that two rights make a right even in California. So, but anyway, this is a sort of a famous quote. And just to briefly sort of give you a flavor of what these mixed methods are. And this is also, these are two, has anybody heard of Juan Simo? Yeah, so he's also one of the prominent researchers in computational mechanics, and has written a lot of very good papers in mechanics. So back to the mixed methods. What are mixed methods? And if you go back, very first lecture in chapter 3 when we were talking about all this, we said that we are going to take this equation. Where did we get this equation from? Equilibrium. This is the equation that says sum of forces is 0, right, at each point. We take this equation, we multiply it with u bar, do integration by parts, and so on, right? So what is stopping us from taking all the other equations also? Let's take this equation, multiply it with maybe, so the corresponding conjugate property would be some virtual stress. You take your constitutive equation, multiply that with a virtual strain, and just keep on adding these terms. So in our case, what we did was all that we did was we took this equation, multiplied it with u bar, and integrate by parts, right? So that's a displacement formulation. You can take this equation, multiply it with u bar, plus take this equation, multiply it with sigma star, take this equation, multiply it with epsilon star, add all of them up, keep on adding things. So essentially what we're saying is enforce all of them weakly. Instead of enforcing these two strongly and the equilibrium equation weakly, enforce all of them weakly. That's a mixed method. And there are mixed formulations like these which people use. And in those kinds of mixed formulations, Taylor was able to show that these two functions are valid choices. Okay, so anyway, so these are basically our higher order elements. And next time, actually, okay, so another announcement is that Monday we will not have a lecture. I'm going to be out of town, so we'll meet on Wednesday after the break. And I'm going to assign this homework 6. So this is not homework 5. This should be homework 6. There are again 3 problems, and essentially what I'm asking you to do is to code up a Q4 general isoparametric Q4 element. And so you can take a look, and I'll be available through email over the break also. And this is going to be due on the Saturday after the spring break. Okay, so you have about 2 weeks for this. All right, so see you Wednesday after the break.